Hi guys, Chapter 6 isn't technically listed here, but just in case you needed a little reminder about what some of these terms mean, I just wanted to pop it in here. This one and the next one are super short chapters, so it won't take very long. So just a reminder, hypothesis is an observation or an idea that can actually be tested. Basically, you're trying to decide whether your observations are true. To start, you need a null hypothesis, and that states there's no difference or correlation between the things that you're measuring except by chance. You want to reject the null. So the null is the opposite of your hypothesis. It says there is no correlation. Your hypothesis says that there is some sort of a correlation. You want to reject the null, meaning you want to prove that there is a difference or a correlation between the two. You can only disprove the null. It's always true all of the time unless you can disprove it. So there's no fine line there. It's either you reject it or you don't. Example, in an OB patient, for example, when a nurse is checking for a gender, the null is that there is no penis, and the hypothesis is that there is one. So if we're betting that it's a girl, our hypothesis is that it's a girl, or sorry, if our hypothesis is that it's a boy, then we should expect to see a penis, right? So if there is no penis, that's the null, all right? So the null means it's got to be something. It doesn't necessarily mean there's a relationship there. It means that the null is just what it is. So if there isn't a penis, then it is a girl. So that's the null hypothesis. We reject the null when we find out the baby's a boy. So statistical significance, the difference you observe between two samples is large enough to conclude that it wasn't just by chance. If your sample size is 2 people, you're assuming that you probably just had it by chance. If your sample size is 100 people, then you can pretty much say that, yeah, right, I don't think this was chance. This is a true correlation. At the beginning of the study, you actually will select an alpha, and it's usually at least 0.05, and that's how likely you are to incorrectly reject the null. So that means you are saying that there is a correlation in your findings when there actually isn't. That's called a type 1 error. So you incorrectly thought there was a correlation when there isn't one there. That means you have 5% chance, which means you have a 95% chance of being correct. And in most studies, 95% is good enough. There are some studies held to an even higher standard, and it needs to be a 97% chance, which means there's only a 3% chance of error. Having a lower than 5% chance means that you are within your error limits that are reasonable for you. So less than 5% chance is a good thing, because it means that you are even more sure that your answer is correct. Clinical significance and statistical significance are actually not the same thing. So clinically different means the differences are large enough to indicate a preferred treatment route. So for example, here's our little option here, and I don't think I can get this down here. Yeah, I can get that down there. There's no effect. Maybe there's a clinically significant effect. Maybe it's a large clinically significant effect. So for example, in our heart attack patients, let's see, or say that there's a clinically significant difference in the outcomes of our patients if they take an aspirin during the first hour of having chest pain signs or symptoms, right? A large enough clinical significance means we would tell all patients who have that problem to take aspirin within the first hour of signs or symptoms of a heart attack. So clinical significance is, again, not the same as statistical significance, but both are important, especially in the medical field. So how do I test my hypothesis? Create and state your null hypothesis and your alternative hypothesis. Your alternative hypothesis is really just your hypothesis. Pick your significance level. So is that 0.05 going to work for you? Or, if it's a deadly drug, then you want something a little higher than that. And then choose which statistical test to perform. That's actually the hardest part, is figuring out what tests to do. Not something you're going to conquer in this class. And then determine the p-value, which is your corresponding probability. And compare that p-value to see if it's less or greater than the alpha you chose. Okay, that sounds complicated. It's not too bad. If the p is greater than the alpha, we fail to reject the null, meaning the null is the correct answer. There is no correlation in what I'm studying. If it's smaller than our alpha, we reject the null and we report the difference. And the reason we report that difference is that it tells everybody else in the scientific community how much risk there is to our assessment. So if your alpha is less than your p, and we know it's a very small number, that means there's really not a very big chance that you're wrong. So that brings us to Chapter 7, which is sample size, effect size, and power. So how many subjects do you need in a sample? Well, it just depends on what you're trying to study. So effect size is the size of the difference between groups that exists in a population. It's inversely proportioned, so as sample size gets smaller, the effect gets larger. And then small effects mean you need a larger sample. The power is the ability to find the difference when one actually exists. So none of this does us any good if we know or we think that there's a great difference between people who wear SCDs and people who don't. If our sample size isn't large enough, we don't have the power we need to prove that difference. So when sample size increases, so does power, and powerhood is the likelihood of rejecting the null correctly. So again, sample size is going to give us the numbers we need to reject the null correctly and not accidentally assume that there's a correlation when there's actually not. We can also have a type 2 error, and that's when you fail to reject the null and you've missed an association when there actually is one. It usually happens because the sample wasn't large enough. We simply didn't see enough cases in order to make the call. Your beta number, and again, you don't have to remember this, but your beta number is the amount of risk you have to make a type 2 error. So this is kind of giving you another example of this in this chart here. Sample size is what you need. You're killing me, Smalls. Sample size is what you need to give enough power to reject the null. So we use a power analysis. What you need to know is the effect size, the anticipated difference you're expecting to see, how much of one error can you handle and still be correct, and then the power is the ability to detect a difference if it actually exists. And again, you don't need to know the math for this. That's not what we're trying to teach you here. I just want you to understand what you're reading when you go through research studies. So this here is actually just an example of all of those different tests. It's an Excel sheet basically that calculates this for you. You don't need to calculate it. You're not going to have to calculate it. It's just one of the ways that scientists work with this data. That's it for these chapters, short and sweet. If you have any questions, give me a shout.